Hello, I wish to show you how to solve a nice little linear ordinary differential equation today with a view to then solving a similar non-linear ODE in the next video. Now, the ordinary differential equation that we're going to solve is the equation here labelled as equation 1. You will possibly notice that this equation looks sort of similar to your average high school homogeneous second order differential equation with constant coefficients that might look something like a y double prime plus b y prime plus c y equals 0. Now, in the case of equation 1, clearly c is equal to 0 and a is equal to x. Generally, that's okay because whilst at high school you were just concerned with dealing with constant coefficients like 3 and 5 or 10 or 1 or whatever, or minus 6 or minus 13. At higher levels, these coefficients can actually become variable. If A, B, and C tend to have X as a variable, or tend to be equal to X as a variable, then it's still a linear ordinary differential equation. But if A, B, or C in this particular case, we'll call this equation 2. So if A, B, or C here in equation 2 happen to be functions of y, then it would be a non-linear equation. At the moment, you can clearly see that equation 1 is a linear equation with variable coefficients. Now, the way we approach equation 1 is a bit different to how we would approach equation 2 when A, B, and C are all constant coefficients. You should know how to solve this type of equation, and that's fairly straightforward and arguably easy to do, depending what your level of ability is. But for equation 1, we have to adopt a slightly different tact. So we'll start off by defining what y double prime and y prime are. And I'm going to write that in red ink, as it were. Now, y prime, as you probably, hopefully will guess, is equal to dy by dx. And y double prime is equal to d squared y by dx squared. The question is whether we write this equation 1 in terms of how it's already written or in terms of dy by dx and d squared y by dx squared. The question remains, how do we attempt to solve it? Because it's arguably more complex to solve than equation 2. Well, what I'm going to do now is move on to a separate sheet. We're going to start by working through the solution to this equation. So I'll just write the equation down once more, and we'll relabel that equation 1. Now, what I'm going to do is rewrite this as d squared y by dx squared plus a over x dy by dx. And that's still equal to 0 because 0 divided by x is just 0. So what I've done is essentially I've divided both sides of equation 1 by x to get equation 2. Now, we can proceed to well, there are two ways of solving this, but let's first of all use a substitution for dy by dx. So I started writing down d squared y by dx squared there. In actual fact, I'm just going to eliminate that, and we're going to write let p equal dy by dx. Okay. This is similar to what I've done in previous videos when solving non-linear ordinary differential equations. So we've got p equal to dy by dx, so that dp by dx is equal to d squared y by dx squared. Right? So straight away, you can see that we can substitute dp by dx in for dy by dx squared, and we can substitute p in for dy by dx here. So what we have is dp by dx plus a over x times p, and that's equal to 0. And we'll call that equation 3. Now, there are two ways of solving this. So I'm going to solve this equation by separating the variables, but you could use the integrating factor method. So to solve this equation by separating the variables, what I'm going to do first is write my p looks a bit weird there. Let me just erase that. So we've got dp by dx, and we're going to put that equal to minus a over x times p. Right, we're going to call that equation 4. So let's go on to the next page. So we'll rewrite that down. So we've got dp by dx equals minus a over x times p. And what did I say that was labelled as? Equation 4. I'll write equation 4 there. So now you can see if we separate the variables out, we divide both sides by p to get dp over p, and we multiply both sides by dx to get minus a over x dx. And when we do that, we have to put in integral signs. So I'm just going to try and write that as neatly as I possibly can. And we're going to call that equation 5. Now, there are two cases to the solution of this equation. We have to consider when a is equal to 1 and when a is not equal to 1. The reason being that you end up with a logarithm if a is equal to 1, and it's not a logarithm if a is equal to anything else. So let's just do the integral anyway for now. So what we have is the log of p equal to minus a log of x plus, and instead of writing down c as a constant, I'm going to write that down as log of c. This is just a matter of choice. You could have just written down c, but I think this writing the constant down as log of c simplifies the algebra a little bit when we come to take anti-logarithms. So we've got the log of p, and that is equal to log of x. And what we can do is we can move this minus a up into the index part of the log of x, so that we get minus a plus log of c. So we've moved that minus a up to become a kind of an indices of the x. So this is a lot easier to simplify now. So we've got the log of p equal to the log of c x to the minus a. So let's go on to the next page. So let's write that down again. We've got the log of p equal to log of c over x to the power a, right? Now we can simplify that by taking anti-logarithms, which is simply, or if you like, taking exponentials of both sides. So e to the log p is equal to e to the log c over x to the a. Let me just have a look. So we'll call that equation 6, and we'll just go onto the page we're on. So that's equation 7, and this is equation 8. So the exponential to a logarithm of a number, say, is just that number. So in this case, we have e to the log of p, which is just p. And that's equal to e to the log of c over x to the a, which is just c over x to the a. And we'll call that equation 9. So we know that p is dy by dx. So that's equal to c over x to the a. And we'll call that equation 10. So let's go on to the next page. So we've got dy by dx is equal to c over x to the power a. And now this is where we have to consider when a is 1 and when a is not equal to 1. Because when a is equal to 1, then we have let me just delete that. We have dy by dx equals c over x. Now this is why we have to consider two separate cases, because when a is 1, we have dy by dx equals c over x, and the only way to integrate both sides of the equation, and particularly the only way to integrate the right hand side of the equation with respect to x, is by turning this right hand side into a logarithm. So what we've got is y equals c over x. Actually, we've got the integral of c over x dx, and that gives rise to well, first of all, let's write this solution underneath. So we've got y equals c log x plus the log of well, we'll call it the log of d, just using d as another constant. So we can simplify that. So we've got y equals c log x. I have to look back at that because I can't remember. Next, plus log of d. Well, actually, let's just erase this c log x, because we can rewrite that c log x as log x to the power c. And so combining these logarithms on the right hand side, we've got y equals logarithm of dx to the power c. Okay, so that is when when a is equal to 1, and that is the final solution when when a is equal to 1, where we've got y equals log of dx to the power c. So when x is not equal to 1, what do we do? Well, let's go on to the next page. So when x is not equal to 1, we've got, we'll write down the original differential that we got. dp by dx is equal to minus a over x times p. And I'll just go back and see what we labelled that equation as. So yeah, I've gone back. That was equation 4. dp by dx is equal to minus a over x p. So I've gone back a bit too much, really, but anyway, we'll do the we'll write down the solution again, so that we've got p equal to minus a. That should be the log of p is equal to minus a log of x plus log of c. So we've got log of p equal to log of x to the minus a. I've already done this on the previous pages, but I'd lost where I was. So what we've got is dy by dx equals c over x to the a. So I really should have gone back to a different equation. So when a is not equal to 1, what we do is, and we'll go on to another page to do this, we've got dy, is that right? dy over, just a moment, dy just on its own, actually. So let's just rub that out. So we've got dy equals the integral of c over x to the a dx, right? So y is equal to c, and actually this can be rewritten as cx to the minus a dx. We write that integral out like that. So you can see that if a is not equal to 1, then what we get when we integrate that expression is cx 1 minus a over 1 minus a. And of course, there's another constant that we add on there. I'll call that d this time. It's a different constant to what we had before. But that is basically the general solution right, there we are. That is basically the general solution to the original ordinary differential equation. And of course there are two, so we'll just write the other one down. So we've got y equals log dx to the c, y equals log dx to the power c, yeah, and that's for a equals 1, and we've got y equals c over 1 minus a x to the 1 minus a plus d, and that's for a not equal to 1. Right, okay. So, yeah, I'll leave it there, and look forward to seeing you in the next video. But thank you very much then. Goodbye.